plastic red cracking. I thought like something serious happened. Like
Full speed?
full speed. She long off. You know what? Bicycle and then going with that scooter. There's a 60.
Okay, we can do that together. So let me just set up this camera and we'll help you momentarily.
That's raining, so. And yeah, I think we really got here.
Hey. So we're going to put it here. Do we need them all? Yeah, I think we can put them all. So this goes here. Okay, and then good. Yep, very good. Yeah, I don't think we need this many because, you know, obviously this is, let's take one piece off here. Yeah. Yep, that's perfect. Perfect. I don't know, probably this screw is not needed because, you know, I don't think that there's that many forces. So, no, you can, okay, we'll do the same. Good. Yes, that's perfect. Thank you. Okay, let me set to see that, you know, how thick it is. I need to switch this a little bit. Yeah, almost perfect. So one last thing to do is this. Good. Alright, so this, let me take a look which end it is. Because this may be mirror, not this one, but this one. Yeah. Yep, now it's perfect. Thank you. All set. So I'm going to close today a little bit earlier than usually. As there's not so much stuff to cover today, so that's the reason. So there's a recap and some new things, but not that many. So we're gonna close at 5:15 or something like that.
5:50.
Yeah,
Okay.
1 hour only. Yep. Good. Did you guys notice that there was a Prime Minister of Finland was walking in that corridor just a few minutes back? You noticed?
No.
Yeah, I was so sure that he will come to follow this lecture, but I guess he decided to follow online. I guess, because he's not here. All right, looking good. So let me just see how it looks when I
Niin, no.
mitä äijät?
Mitäs tässä? Miksi tää pöytä talle on siirretty? Tää tässä pöydällä tätäkin.
No meillä on kato eri virittäjät tänään paikalla.
Kyllä.
Sen takia. Mutta jotain nyt ei ole vielä. Ai joo, mä tiedän mikä siellä on väärin. Siellä puuttuu toi taustakuva.
Pitää taas varautua mutkasvaiheessa ne kuvat.
Joo. Ei se nyt niin hirveet. Huomasitteko te, että Petteri Orpo käveli tuossa, no etti, että missä hitossa on se luentosali, mistä tää meidän luento alkaa?
Oliko tää taas Orpo töihin
En, joo, vissiin kai. Joo. Kyllä. Ja säkin katsoit tämän lauantain niinhän se on. Joo. Joo, ei ole ihan näköä täydellinen. Se jotenkin nyt kroppaa noita reunaa. Pitää katsoa, mikä siinä nyt on. Niin jo. Joo. Ai jaa. Joo, en kattonut sitä. Ei ole vieläkään ihan täydellinen.
Se oli tosi paljon sille se henkilökohtaisia mielipiteitä, että
Ai jaa.
niin ei jättää silleen hallituksen, että ei jättää vähän silleen outoa.
Niin joo.
Suomeen sinne edustamaan, mutta
Niin.
puheena niin ruvetit on.
Mutta tiedättekö, mikä yliopisto on kunniatohtori Stubb on?
Eikö se ollut harvoin? Eikö missä?
Ei, parempi.
Oli jossain jengi.
Ei, kun vielä parempi. Alkaa L:llä. Seuraava on U. Mikäs tulee sen jälkeen? Lut. Oh. Joo. Kyllä. On joo. Lutin kunniatohtori. Nyt ollaan ihan väärässä päässä tätä.
Kato, mä voin siihen mahtuisi 3 eri tukea. Ja sitten voisin ihan hyvin katsoa moottorikäytävän, voidaan kaivaa. Vedet perään.
Ei kyllä mä enää 3 henkeä siitä.
Eikö? Koira pois, tuon kolmesta.
Se sentin vesivarra on kyllä vähän.
Oli siinä 2.
No vitsi.
Eikä meissä, siis ei meissä mietitty.
Tai ei. No joo. Kerran oltiin vähän liian kyljettyä sitä autoa vastaan.
Ei paljon hyvä.
Ei paljon, mutta meitä se käy aika lähellä.
Sain tänään influenssarokotuksen. Ne on jotenkin vähän niin kuin veto pois. En tiedä miten, vaan onko vaan muuten vaan veto pois. En tiedä. Heti aamulla ihan ensimmäiseksi. Ensi viikolla on sitten välikoe.
Onko vaikea?
Ei ole. Suosittelen, mutta mä sanonkin tuossa, muistuttakaa jos en muista sanoa, että kannattaa käyttää ChatGPtä, mutta sitten vielä enemmän kannattaa käyttää niin sitä symbolista MATLABia tai mitä nyt ikinä sitä tykkäätte käyttää, koska se minkä takia myös sanotaan, että käyttäkää ChatGPtä, niin on tietenkin se, että se ei pysty laskemaan niitä oikein. Niin, se on tietysti sitten, kun siellä on niinku vaihtoehtoja ja muuta, niin voihan sitä niinku arvailemalla. Voihan se Tuurillahan ne laivatkin seilaa, vai miten se menee? Siis kaikkea. Ainut mitä ei saa, niin, ja se nyt ei hirveästi hyödytä, niin kuin, että tehdä porukassa ja muuta, koska ne on aina erilaisia ne kysymykset. Että se on sellainen. Mutta muuten saa käyttää, niin kuin, ja suosittelen, että käyttäkää kaikkia. Se on se ChatGPTkin sikäli, että se tarjoaa sieltä jotain. Mutta siihen ei voi luottaa näissä laskujutuissa, että se myös testattiin, että se antaa sieltä, niin kuin, voihan se osua oikeinkin, mutta tyypillisesti menee väärin. Niin ja sitten siinä on sellainen, sähän jos teet silleen, että mikä tässä on oikea vastaus, se on vaikka toi A kohta, ootko varma, tarkista se, ei kun B, ootko varma, ei kun C. Ja sitten, että ootko nyt varmasti tarkistanut huomioon, että hyvä pointti, nyt se onkin D. Niin, joo, just niin.
Onko ne niin miten samanlaisia noihin viikoittaisiin tehtäviin?
Ihan samanlaisia. Ihan tasan samat. Et sen takia sitä kirjastoa on siellä mukana. Et sit sieltä vaan, niin kun tulee se tehtävä, niin sinne hakkaa ne. Siellä on tietysti niin järjestykset ja muuta, voi, niin vaikka rajoiteyhteydet, niin ne ei ehkä mene samassa järjestyksessä. Mutta kun etitte sen vaihtoehdon, missä ne on kaikki oikein, niin se on sillä selvä. Joo, kyllä. Mutta kannattaa käyttää, miksei sitten ChatGPTstäkin, mutta siihen ei kannata, niin kun me se testattiin, että mitä se toimii siinä. Koska ei muuten tässä olisi mitään järkeä. Muutenhan se kaikki, niin kuin nyt tietysti aika monessa kurssissa, niin ei siinä ole mitään järkeä käyttää nettitenttiä, koska ChatGPT tekee sen niin älyttömän hyvin. Niin se on. Katsotaan vielä, miten tuo leikkaus tuon kameran mun päät. Tässä on nyt pitkä viive tänään. Eiku ihan hyvä. Okei. Okay. Yes, it is respect. It is a time to get started the lecture number 7, ID 7. And this is it. This is the last lecture before the midterm exam. So the thing's getting hot and heavy. What do you say? No. So we're gonna summarize pretty much everything we have discussed so far. There is going to be one new subject matter that I would like to explain to you, and that is constraint stabilization. We will take a look at the MATLAB examples that I showed you a week ago, because some of them, at least one of them, wasn't very successful, and now it's going to be successful because I trained myself prior to lecture, so it should be going well. And of course, should be. Let's see how is the DMO effort today. And I'm hoping we're going to close the lecture today already at 5:15 or roughly that time, and then we're going to go for another session, which is this Q&A session, getting started today at 5:45. And first half an hour or so will be in Finnish, another latter part will be in English. So any unclear matters, please join in and we can discuss. But today what will follow is a discussion about what is that I'm expecting you to know when you enter in the midterm exam. Already this time, I advise you to take all material ready with you. That includes the lecture note, weekly assignments, ChatGPT, so on and so forth. Make sure everything ready. And I say this because and we would not allow you to do this exam online if not knowing that the ChatGPT is not able to solve this completely correctly. It can, maybe some of the things can go correctly, but I highly recommend that you have this library in this mathematical library that you can do the symbolic computing, because that's more reliable, significantly more reliable than ChatGPT. ChatGPT can do it by luck correctly, but we tested that is not consistently correct. So, highly recommended, highly recommended. And there are, of course, it makes sense to ask, from ChatGPT, what do you think about this? Can you give me the right answer? And we'll see how it's going to go. Okay, But today, one more thing that we need to discuss is constraint stabilization. It's related to the way the constraints are taken into account in the equations of motion. So that's what follows today. So, but prior to that, let's discuss a little bit what we discussed a week back. So a week ago, we discussed about the concept of virtual work. The concept of virtual work is often misused, and is very often misused because this what's come after from the concept of virtual work. So this is a force multiplied by displacement. This time, virtual displacement. You know, usually this is misused because when you introduce the virtual displacement, this delta Q, you can set this equation to be equal to 0 only, and only if your virtual displacement are kinematically admissible, meaning that it not need to be kinematically possible displacement. The way the virtual displacement I expressed here is that I'm going to introduce the virtual displacement to all my generalized coordinates, and I don't care about the constraints. And that means that this equation is not going to be 0. And that's simply because when you do so, then the reaction forces due to the constraints will do a certain amount of work. And that certain amount of work is not accounted here. So the obviously constraint forces or reaction forces due to the constraints are not accounted. Let me repeat it. So the concept of virtual work is often misused because that concept you can find an equilibrium. You can set this equation to be equal to 0 if your virtual displacement, which is let me take some drawings away, which is this guy here, is expressed in a way that is kinematically admissible. Here, like you see what we do here, this is not kinematically admissible because what we do if we have a system for one body, so we introduce the virtual displacement for Rx, Ry, and angle theta. That means that if I have a pendulum like this, I'm going to introduce the virtual displacement that the system is moving like this. That's not possible. This is not kinematically possible displacement because I'm going to violate against the constraints. The same if I'm going to move it along this guy, Ry. So it's going to be like something like this. That again, violate against the constraint. Theta, depending how we're going to set the body reference coordinates, might not violate against the constraints. But look what I do. I'm setting my virtual displacement to all the generalized coordinates, not just the one that is kinematically admissible. And that's the reason that this equation is not going to be 0. So we can force this equation to be 0 in two alternative ways. First of all, we can express this. It is possible to express this virtual displacement such that it's kinematically admissible. How that's going to go? That's going to go, of course, with help of the constraints. So with help of the constraints, we are able to identify the number of coordinates that the virtual displacement can be imposed to. And we can make it in a way that is kinematically admissible. But that's going to be another story, completely another story. And that method is actually something that will be based on coordinate partitioning. And it will lead to minimum number of differential equations. Minimum number of differential equations would be the number of degrees of freedom. In case of the pendulum, it will be one differential equation. Now we do not do that here, but instead we are adding the constraint to this equation with help of Lagrange multipliers. And that was based on this optimization problem when we are finding the optimum such that the constraint is accounted. We are able to do that by taking a Jacobian and the corresponding vector, which is the Lagrange multipliers, into account. And that's it. Now you can set this equation to be equal to 0. So this was alternative. Okay, and this was called augmented formulation, or more correctly, the method based on Lagrange multipliers. What we do then? This is very important. We are adding the number of unknowns, because originally this is going to be our unknowns, and in the case of the pendulum, it's going to be 3 generalized coordinates because everybody needs 3 generalized coordinates. Correct. And then what is going to be unknown too is going to be reaction forces. Reaction force is going to be equal to the number of independent constraints. Here in this case of the pendulum, we need 2 constraints. So the number of unknowns will be 5. Because the 3 generalized coordinates plus 2 constraint equations, that's going to be a total of 5. All right? Makes sense? Makes sense. All right. Now, what we then concluded that this equation alone is not enough for us. Why that is not enough? Because this is an unknown and this is an unknown. We have this amount of equations here. So we have too many unknowns versus the number of equations. So we need to have additional information. And the additional information, we can get it by taking constraints into account. So now we have a matching number of unknowns and equations. So we're good to go. Still, a little bit of problem is that this system here is called as a system of differential algebraic equations, which can be integrated in forward of time, but there is not that many integration schemes available compared to ordinary differential equation. So what we do then is that we're going to take this constraint equation, differentiate that twice with respect to time, and substitute that to this equation. And now we can express everything in terms of ordinary differential equation. And now there is plenty of choices, Runge, Kutta, fourth order, or whatever you want, that you can solve this in forward of time. And that's what we're aiming for. And then we had this example, this is how the equation of motion finally look like. And just a summary, this is a mass matrix, this is a Jacobian matrix, Jacobian with a transpose. This is an acceleration, reaction forces, which is Lagrange multipliers, generalized external applied forces, quadratic velocity vector, which is going to be equal to 0 if body coordinate system is located in the center of the mass, and the QC that came along when we differentiated constraints twice with respect to time. Now, this was an example we looked last week. So this was kind of like a pendulum system, but in the difference at the P, there was a primitive joint, and at Q, there was a primitive joint. And the equation of motion looked like this. So this is something that is called system matrix that need to be inverted. And then it needs to be multiplied by forces, which is this vector here. And I saw the response, but the response was incorrect because I made some changes in my constraints, and it was actually a pendulum instead of the system like this. Now I wanted to show you the fantastic animation that's gonna get the great start for today's lecture. That this is gonna be me solving the same problem using the MATLAB. Where is my MATLAB now? MATLAB is somewhere hidden behind. Hold on. I need to take this. Where is it? This is, I don't want to. Where is my MATLAB? That's the one window, but I need more than that. Where is it now? No. It's hidden somewhere in the back. Very much in the back. I cannot find it at all. This was my browser. There it is. Okay, so I'm gonna put the camera back. It was this guy here. So now the only participants can see us, and I'm gonna solve this response like this. And it's done. What is this? What is this? So why is that I cannot? So again, what did I type here? Did I type this incorrectly or what? Look at that. So I mentioned this possible demo effect that I wasn't sure that it can be that bad. So where is the window that this response is hiding? So let me see. No, there is something off. There it is. And again, it is okay to get emotional because this is one of those big deals in your life. Remember when you learned to do the kinematic analysis, it was a big thing in your life. Now what is this? Bigger, much bigger. So what we did here was solving the dynamic response. And yeah, you might see that, okay, there is like a ridiculous beam-like body that is moving around, like what difference that makes in your life. I can tell you this, big difference. Because now you have the skills to create the equations of motion for any kind of mechanical system. Because you can have much more than one moving body. You can have any number of bodies you want. You can combine them any ways you want when you combine them with the help of the constraints. How this is going to go in details, this is something that Alfonso promised to explain to you tomorrow. Tomorrow there's a guided tutorials, and he's going to show you, okay, this is how it's going to eventually go. Like, this is how you can compute each of the components. We look at the equation of motion symbolically, and how you can convert this symbolic computing to be numerical time integration in forward of time. And that's what you're going to learn. That will be tomorrow. Good. So that's kind of like one of the highlights of this class, but there's going to be more, even more than that. Because what we're going to do then is that we're going to eventually add some hydraulics to the system, because we need to know the forces that is imposed to the system. And that's simply because, if you think about, if I take myself back to the Newton's second law, like the external applied forces is equal to the inertial forces. And D'Alembert figured out that this can be written like this. All right? So now what we do with this equation, or maybe it would be better to say this equation, we're solving this r dot dot, which is simply like basically like this. And then from r dot dot, we're going to solve the velocity and then position. Now, what happens if you do not know this guy, externally applied forces? What's the value of your response? No value, because it's just imaginary stuff. It's not related to reality. So the latter part of my course will be focusing on this F component. And we're going to look at how this can be described by using hydraulics. If we have a time, we can take a look at how that can be described by other means of actuators like electric drives and pneumatics. Okay, but anyway, so that what follows a little later. But now, here's my first in-class quiz. This example, which consists of 1, 2 moving bodies, and then 1, 2 revolute joints. So it's a total of 2 revolute joints and 1 primitive joint. What's going to be the number of unknowns? This is something that I think that you can try to solve this by using ChatGPT. And ChatGPT may be providing the okay answers in cases like that. I might try by myself. I have, by the way, the professional ChatGPT, the one that is the paid version. I guess that you guys don't have that. Or do you? No. Okay, so I'm going to take my professional ChatGPT. I'm going to take a picture of this and asking what's going to be the correct answer. Okay. What is correct option? Okay, and let me see what is responding. This, I'm pretty sure that it can make it correctly. Now let's see. Let's analyze. So he's analyzing. So he's figure out that this is planar linkage. Very good. So it's really going good. So he's able to figure out that there is a, okay, it's give me the 4 revolute joints. You think that's correct? I don't think so. So it's able to figure out 4 revolute joints, substitute then, so the mechanism has a 1 degree of freedom. That is correct. That's correct. That's correct. Each revolute joint introduces 2 unknown reaction forces. So the answer is B. This is what came out from my ChatGPT. So ChatGPT is saying that must be B, and the reasoning is, or he or she would like to explain why it is 6 instead of 8. That's another option, but the 8 is not in one of these options. So this is what the ChatGPT is telling me. So this is, again, you can use the ChatGPT and it is recommended. Please go ahead and use it. with caution. Be careful with it. So now the ChatGPT is voting B. You guys agree with the ChatGPT? No. But ChatGPT is better than any professor in any universities. Okay. So you put your answer on, and should we take a look at this immediately or a little after? You guys ready?
Yeah.
Okay. Let's take a look at this immediately. So this is my Socrative here, and we got 68. Okay, the number is increasing 71 answers, 73. And again, for online participants, 2, ChatGPT is proposing that is 6 as 6 generalized coordinates. Okay, 82. So are we done? Number is still coming up. This is really good news, because if there's this many people following the summary lecture, it provides typically very good outcome from the midterm exam. So are we going to reach all the way up to the 90? No, but close to that. The correct results is, this is what we discussed a week ago. The correct result is 11. So somebody was trusting that the ChatGPT knows the way to go, and it was incorrect. And the funny thing is, it was willing to explain me why it is 6 instead of 8. Like, makes no sense. Okay? All right. So, lesson learned. You guys have a bigger brains than ChatGPT. You need to trust yourself and make sure that it's fine to ask, like, what do you think, ChatGPT? What is the correct answer? But don't trust on that. Think about by yourself. Look at the next lecture notes and make sure that you have this math ready in these scripts. Okay? All right. Now, constraint stabilization. This was something that I showed you a week ago, so let me take myself back to the this one here. And this was so this when we look at this crankshaft mechanism, the crankshaft mechanism looked like, let me take this away. So it looked like this. That's how it behaved. That's a correct behavior. But what I did in the very beginning was that my integration settings parameters were not set properly. And what happened when I did that was, so now I need to take a look at this is I had an error tolerance that was really, really big. So I was saying that I don't really care about the correct results, so just compute me something. And that happened when I said that, okay, just compute me something. And this is the response based on that. What's happening here is that the constraints are no longer fulfilled. So this is I'm violating seriously against the constraint, because this end is supposed to be here, and it's not. It's not. So why is this? Why is this happening? And this is what I would like to explain to you next. Why this is happening? And this is happening because of the following reason. What we do here, remember when we were converting the differential algebraic equations to be ordinary differential equation, we did this with help of constraints. And to be more specific, we did this by differentiating the constraint twice with respect to time. Okay, a physical interpretation of that is clear, because what we do here is that we including the constraints in velocity level to equation of motion. Velocity level. All right, so what we do then in equation of motion, we are coming from the, excuse me, I say incorrectly, in acceleration level, of course, because it's a c dot dot, acceleration level. Now what happens when we do this in acceleration level is that we are integrating the velocity level, and when doing so, we might introduce a certain amount of integration errors. And then when we come down to the position level, we make another set of integration errors, which typically accumulates. They keep on adding, so they are not able to get rid of these errors. When they are accumulating, the system started to violate against the constraint. We need to do something for that. as something we can do, or what's actually the big, where this is happening. Those of you that were paying attention to mathematics in high school they explained this integration. When you're integrating from acceleration to velocity, there's going to be something that is a constant value that will be added to the solution. And constant value is the one that depends on initial configuration, initial condition. We don't take that into account. So we're just assuming that this guy here is insignificant, is equal to 0. The same happens when we go for velocity to position level. So we have two integration constants. This integration constant would never introduce the equation of motion. And because of that, we're going to have quite a bit of errors, possible errors. We could get rid of this by setting that, okay, make sure that the integration tolerance is high enough. Let me correct myself, small enough. So it's going to be tight enough that the error introduced each of the time we do this switching is going to be insignificant. That's going to be the one way to do it. Or we can say that, we can alternatively take these A's into account. Each of these ways are not going to be very practical in reality. And that's why there's something that is called constraint stabilization. And constraint stabilization is something that we adding extra forces that are not because of the reality, but they are just to make sure that we are not starting to violating against the constraints. And one of the most used one is a bump cut destabilization. Now what we do in the bump cut destabilization, and look where this bump cut destabilization is going for, it is going for the forces. It's going to be one additional force that is added to system. And it's going to be introduced in such the way that acceleration level is like no changes. It's going to be exactly like I introduced that a little while back. But then in the position level, and actually in a velocity level, position and velocity level, I'm adding constant values that are alpha and beta. And they're acting like a spring and a damper. And it works like this. So if there is like let's take a look at this pendulum again. So as soon as the pendulum started to move, let's say like at this direction, what comes into play is going to be a spring and the damper. And they're bringing this back where it was. Of course, the violence is not going to be as big as I make a drawing here, but it takes it back. So the spring force is back where it was, and the damper makes sure, this is what I wanted to draw here, is a spring and damper. Spring takes it back where it needs to be, and the damper makes sure that when it do so, is not starting to vibrate, but is just doing the motion back where it's supposed to be, and that's it. And that's going to be handled by these two additional force components. This is going to be my damper. This is going to be my spring coefficient. And when we do so, this is something that is going to be stabilized. And when we're going to properly select the alpha and beta, then the system will not violate against the constraints. How that sounds? Pretty good, I would say. Yeah, why not? This makes sense. Makes sense. Okay, and that was last thing that I would like you to be aware of prior to midterm exam. Okay, now what follows is that I'm going to explain each of the subject matters that I'm expecting you to know in a midterm exam. And then we're going to look at the practicalities, like how you actually enter the exam. And then again, you have this opportunity to ask questions a little later today. Okay? And then if you still want, but that need to be like encore or something like that, I can explain the multi-body system dynamics to you in 10 minutes, max 10 minutes. But you need to clap your hands like seriously to make me to do that. Like in a rock concert, like the same thing, because I make this ready encore. But it's up to you guys. So we'll see how it's going to go. All right, so recap. These are the subject matters. So these are the things that I'm expecting you to know. And I know that you're busy. You have your 400 euros car and you're traveling and I don't know. And you cannot focus too much about the midterm exam, so you need to find shortcuts. Why not? So I have a shortcut for you. Shortcut is this. Each one of these subject matters are rated by stars. Higher number of stars, the more important it is. So please get started with the ones that are highly rated and forget about the rest, because I know you're busy. And some of you might not consider this as a very important course, and you're happy if you're going to score one out of 5 from as a final grading. Fine. So then just focus on the ones that are highly rated. Leave the rest with no attention at all. You can try to guess the correct answer with help of the ChatGPT, or you can try to read that from a lecture note. Those are the 2 possibilities. Okay. All right. Description of planner body. That's going to be, the same rating than hotels. 5-star hotel is the best you can find. There is no better than that. This is a 5-star hotel, so it's really fancy, very, very nice. So it's a best. Okay. Description of planner body. This is how it goes. So we discussed that in this class, particles, bodies will be described with help of the body reference coordinate system. Body reference coordinate system is attached to the body. Is rigidly attached. So if the body translates, so do the body reference coordinate system. And if the body rotates, same gonna happen the body reference coordinate system. Now, because of this kinematic notation, so we're gonna have 2 components. The one that is describing the translation of body reference coordinate system, which is this guy here. And then we have a rotation of the body reference coordinate system with respect to global coordinate system. Rotation will be described by 2 by 2 matrix, where the columns of the matrix describe the axis of the body reference coordinate system. So these 2 vectors are orthogonal and perpendicular, meaning that they are perpendicular with respect to each other, meaning that there's a 90 degrees angle between these 2 vectors. They are also unit in length, that is the case of the body coordinate axis. Okay, that's the first thing to know. Spatial body, 3-star. That's a okay quality hotel, but not the 5-star, but it makes sense. If any extra time left, focus on this too. Same story, no difference. There is one big difference, however. This one here consists of 3 components. This one here can be described by multiple different ways. And we discussed about one way to describe 3 by 3 rotation matrix, and the one way we discussed was based on Euler angles. For your information, one of the most used are quaternions, which is based on 4 parameters and 1 constraint. This is what is typically in each of the computer software that are dealing with the rotations. Computer game that some of you might have tested, probably not using too much, is going to be their visualization is actually based on quaternions, not the Euler angles. Okay, Euler angles goes such the way that we have 3 successive rotations. So 1 rotation after another. That's what the successive means in this case. So the first rotation takes place around the z coordinate axis and is amount of P. What is this? P. I forgot this already. Okay, but you can read it by yourself, so I don't need to repeat that. So that's going to be the first rotation. Second rotation will take place once rotated coordinate axis x, and that amount of rotation is theta. Then we have twice rotated coordinate system, and then we're going to introduce a rotation around the z coordinate axis, this time p. Yeah, that's what I say, pi. So that's going to be that one, the third one. And now we have a rotation describing each one of these rotations and how we can get the final one by multiplying them together. Whatever you do for a midterm exam, please do not memorize any of this kind of stuff. That's going to be a big waste of time and energy. We'll never ever ask anything like that. We just don't. All right, velocity, okay, that's a 2-star hotel. So it's okay, so there's a breakfast available, but not the greatest one. And the bed is okay, so you can sleep overnight, but not the greatest. Okay, the velocity, it consists of 2 components that are translational velocity and angular velocity. This one was the one that rotation was added 90 degrees angle, and that's how you can get that from your original rotation matrix. Acceleration, also the same thing, so it's going to be 2-star hotel, so that's not too important. Consists of 3 components. Translational acceleration, then there's one component that is quadratically related to velocities and angular velocities to be more specific. That's going to be normal acceleration component. And then there's going to be tangential acceleration component due to the rotation. And these two is due to the rotation. This is due to the rotation. And that's how the acceleration look like. Again, if you are busy like you are, I know you guys are busy, so forget about this. Don't focus on that. Okay, generalized coordinates. Okay, that's obviously is one of the good hotels. So like this city, Lappeenranta, the best hotel you can find is a 4-star hotel. So this is it. So it really makes sense to look at this. Generalized coordinates comes from this equation that is describing the kinematics. Now what you need to do is that you need to be able to identify the variables. The variables are components of this guy, because this guy is a vector. In a planar case, it consists of 2 components that are Rx and Ry. And then the components that is associated to rotation matrix, that is angle theta. Vector U bar consists of U bar X, U bar Y component, but they are not variables. They are constant numbers, constant vectors, because we are assuming the body to be rigid. So the vector U bar cannot change as a function of time. Okay, so this is a vector of generalized coordinates, and we discussed about what everybody needs. So what everybody needs. More than love, we need 3 generalized coordinates. Okay? So that's it. We continue with the high quality hotels. So the next one is constraint equations. Constraint equations are the equations that are limiting the motion possibilities. Make sure that you're practicing this. Make sure that you have scripts ready for different scenarios in the case like this. And pay a lot of attention where the body reference coordinate axes are pointing to. That's very, very important, because we see a lot of mistakes that you are not looking carefully how are the coordinate axes. And sometimes it can be surprising, like there could be beam-like body and the y is pointing in a direction of the body, and x is pointing transverse direction. So now I'm going to leave this to your responsibility to make a close look about each of the cases. Take that really closely. Ask your friend ChatGPT where the axes are located if you are not able to figure out by yourself. I think that ChatGPT can do that, if nothing else. And then very careful when you're setting up the vector U-bar, because this is where you can make a lot of mistakes. All right? And then we have here another concept that is a number of degrees of freedom. So we have 3 different scenarios. So we have the one that is a dynamic system, where the number of degrees of freedom is more than 0. 1, 2, and so on and so forth. And that's going to be something that is dynamically driven system. So you have to create the equation of motion to solve the responses. It could be kinematically driven system, kinematic system, where the number of degrees of freedom is equal to 0. And you can solve the responses using constraint equations only, nothing but constraint equations. And the redundant system of a constraint system is something that the number of degrees of freedom is less than 0. Redundant is something that there is constraints are not independent. Have you ever guys been in a hotel like this? What is in Dubai? Is it so that in Dubai they have a hotel that is having the more stars than 5 stars? Is that? How many stars they have? 7. That's nothing. Nothing. So in Burj Khalifa they have 7-star hotel. Yeah, but look what we have here. So we have here 2, 4, 6, 12. Burj Khalifa, only 7. Only 7. That's ridiculous. That's nothing. That's absolutely nothing. So we have here the hotel that is better than ever before in this planet. Okay, planet Earth. So you're going to see something completely different here. And that's a hotel 12 stars. Okay, what's the deal with this? Jacobian matrix. Now, very careful with this. Make sure you have a script ready. Make sure that you know how to create the constraint equations. Make sure you understand everybody needs 3 generalized coordinates. And then that's everybody. So if you have 2 bodies, it's going to be 6 generalized coordinates, so on and so forth. And then do the differentiation automatically. Don't try to do it by yourself with a pen and paper, because for sure you're going to forget like what's going to happen when you differentiate the sine theta or something else. It's very prone for errors. So don't do it by yourself. Of course, you can go anywhere you want, but highly recommended. Please use the help of symbolic math tool. Not ChatGPT, but the symbolic math tool. I'm not sure if ChatGPT can make a mistake in cases like this. That's a little bit unclear. I have never tested. Okay, back to the Lappeenranta. So we have 4-star hotel again. So we have kinematic analysis. Kinematic analysis consists of 3 steps. First, we're going to solve the position level analysis, which is a iterative procedure. So we solving something that is called Newton difference. Newton difference is not the solution, but it's a direction how to update our generalized coordinates to get a better estimate about the solution. And you keep on doing this until you are getting close to the final destination that you can evaluate based on how big is a Newton difference. Once it becomes to be small, you're reaching your final destination. Velocity level is nothing but the substitution. Substitution. Acceleration is nothing but the substitution. But there is a little bit of involving components related. But that's okay. Generalized forces, we become to be a 3-star hotel, which is okay. So the concept was like this. So we start with the concept of virtual work. Virtual work, like any other work, is a dot product of forces and displacement. Forces, displacement in the direction of force. Okay, this is our force, this is a displacement. We did this because in the case of virtual displacement, we are assuming that the time is not running. When the time is not running, we can express this delta R with help of delta Q. And that's what we were aiming for. The whole concept about the virtual work was nothing but finding the relation between global coordinates and generalized coordinates. This relation is this partial operation matrix that is obtained by using partial R, partial Q. That's what we're aiming for. And when you're using this mapping matrix, you can express your force in terms of generalized coordinates. Originally, your force vector, let's say the gravity force, will consist of 2 components. Once you do this magic mapping, it will have 3 components. Why? Because everybody needs 3 generalized coordinates and the corresponding number of forces. External applied forces and inertial forces. You just cannot mix these things. You cannot. All right, so that's it. And then comes this big nightmare about how you do the same, but for inertial forces. Same story, so it's somewhat important. First, you are expressing your acceleration in such a way that you clearly differentiate your acceleration. I mean, generalized coordinates acceleration is here, and this is the one that is quadratically related to angular velocities. This was this mapping matrix, and when you substituted them all, you're gonna get the generalized generalized inertial forces. The generalized inertial forces consist of 2 components: mass multiplied by acceleration and quadratic velocity vector. This is how the mass matrix look like. So it is a 3-star hotel. So it consists of 3 different components: The one located in upper left corner is going to be identity matrix, where the identity, which can be not identity matrix, but the diagonal matrix, where the diagonal components are mass of the body. These are related to Rx and Ry generalized coordinates, translations. So it makes sense. Then the one that is located here in the lower right corner is going to be the one that is related to orientations and angle theta only, and it's going to be mass moment of inertia. How much the body resists the rotation, inertia-wise. And then the one that is going to be equal to 0 is the off-diagonal component that translation of velocity, but this is going to be equal to 0 if body reference coordinate system is located in the center of the mass. Quadratic velocity vector was like how much body reference coordinate system feels the rotation force-wise. So it's like centrifugal forces that is imposed to the body reference coordinate system. If the body reference coordinate system is located in the center of the mass, it feels nothing. Nothing. If it is another end, it feels amount that is related to, quadratically related to angular velocities. Makes sense? But 2-star hotel, I don't know. I guess it makes sense to skip this. Augmented formula is we back to the best of the best. So we came back to the 5-star hotel, the whole concept. You know, how we added the constraints, the original equation, and also with help of Lagrange multipliers. And that all happened with the help of the Jacobian matrix. And when we then take the constraints into account, and we converted the whole system to be ordinary differential equation. That's the whole story. And this is how it goes. Okay, this is, I'm sorry. I thought that I corrected this already when I edited my slides, but I did not. So exam will not be available until Monday, October at 1 minute after the midnight. So it's going to be available right after the midnight. So I don't know how is your daily rhythm, but I guess you guys are not sleeping that time, or are you? This is not far when I woke up. Not exactly that time, but you know, anyway, so you can make your first attempt right after it becomes to be available. And then it's going to be closing on Sunday, 26th of October, 1 minute before the midnight. Now here's the thing that is unclear to me. Is it still allowing you to do it once if you are able to start it before the midnight? I'm not 100% sure about that. So just to play safe, get started at least 2 hours before the midnight. So 10 o'clock, latest on Sunday. So then you will be safe. So again, so once you do your attempt, you will see the points, how much you're going to score. And if you're happy, that's it. If unhappy, keep on reading, keep on practicing, keep on doing the scripts, and make another attempt. Okay? And what matters? Look at this. Highest grade matters. So it doesn't mean that even if the first attempt is equal to 0 out of 5, that's fine, because you still have another one left. So, and if any technical difficulties, please reach out to Murica. Murica is going to help you with if any technical difficulties. Let's practice. Okay, if this is an orthogonal matrix, then the transpose of the orthogonal matrix multiplied by original matrix, another way around, is going to be identity matrix. However, it is not necessary that the vectors made out of the columns will be perpendicular with respect to each other. So this is it that they need to have a 90 degrees angle? Is that the case or not the case? Read this carefully. Read this very, very carefully, because sometimes the wording can be confusing. But what is it? True or false? And it's going to be available in in-class quiz. So we practice a little bit about this midterm exam. Okay, guys, you're good to go. True or false? is not necessary. It's not necessary what it's asking. True or false? True or false? All right, so let me take a look. So we have 32 answers so far. So we and the counting, so it's getting to be 50 and more. Okay, let me ask what the ChatGPT is saying for this case. I'm pretty sure that it cannot miss this. What is correct? Okay, ChatGPT is telling me that it needs some longer thinking, so it's not so obvious. And again, I have this super nice commercial version of ChatGPT, which is ChatGPT 5. Okay? You guys ready? Okay. Implies are orthonormal. Each column has unit length. Are perpendicular to each other. Okay. Should we go? Very good. Very good. Very good. You know, I think what matters here is that the wording, you need to be very, very careful to make sure that you know what exactly is being asked. Okay? Let's practice a little bit more, and then we are almost good to go. Next one. My favorite. How you describe the particle rotation. Particle does not have a rotation degrees of freedom. With help of rotation matrix A, with help of R, with help of generalized coordinates. Let me take a picture of okay, first let me put it on, and then I'm going to take a picture using the ChatGPT. And I'm pretty sure that ChatGPT can do this all correct. Okay? I'm going to put this back. Okay, ChatGPT, what do you say? What is the correct? And the answer is option. What is the correct option? And the ChatGPT is telling me thinking. This is not. Huh. Some very, very surprising explanations. I'm going to read it to you once we're done with this. Okay, you guys, what do you think? What is the correct answer? What do you guys say? And we got the 52, 54 answers so far. Hmm. 60, 70. All right. Now, like I said, the Prime Minister of Finland was walking in a corridor just before we started the lecture. I think he would be very proud of you guys if you score 100%. So maybe we can call him back and take a look and shake each of your hands. Hey, good job, guys. So what do you guys say? What is the correct answer? Are we going to 80, 84 answers, 85? Okay. Let me read what ChatGPT is telling. Correct answer. A, particle does not have a rotational degrees of freedom. Interesting. Okay, guys, please trust ChatGPT. Please, whatever ChatGPT is saying, that's the way to go. That's the way to go. Here it went correctly. It went correctly, and it says that the explanation was absolutely correct. Absolutely correct. A particle does not have a rotational degrees of freedom. Explanation. A particle in mechanics is treated as a point mass. It has position but no orientation. Look at that. Way to go, ChatGPT. Therefore, it cannot rotate or possess a rotational degrees of freedom. Way to go. So it's all correct. All correct. Okay, the last one. This one. Physical interpretation of Lagrange multipliers. And then let me see what are the options. I'm going to take a look at that. And that's the last of the day. So the options are force is due to the inertia. Force is due to the inertia. Acceleration of generalized coordinates. Rotation of the particle. Here it comes again. Rotation of the particle. Reaction force is due to the constraints. And let me go and ask from the ChatGPT. ChatGPT, what do you say? What is the correct option? What is the correct option? ChatGPT is telling me thinking. This too is a He's saying guess what he's saying? Not C, which is good news. Really good news. Okay, let me take a look at how you guys are doing here. So we got 60 answers so far. 66. Good. '73, 74. What was the count in the last in-class quiz? I think it was 80, 85, 84, something like that. So soon we're going to be there. So I'm going to close this momentarily. Okay, so we got 80. And now just a couple more and then we're done. Do you guys think that this is going to be 100% success rate? No? No. I don't think so either, but I think it's going to be high, but not 100%. Quite high, quite high. Okay, so correct answer, and this is what the ChatGPT was making correctly. So it was saying that in Lagrange formulation of mechanics, Lagrange multipliers represent the forces that enforce the constraint equations. Very good, very good. Acceleration of generalized coordinates is very much incorrect. Forces due to the inertia are generalized inertia forces, not the one that I was asking. All right? Good thing. And that was it. That was it. Yeah. That's it. Good thing. Now, I really would like to go with this encore, but we don't have much of a time. And you guys are doing no reaction. You do no actions in that regard. So I guess that you don't need it. You don't care about that. I understand. I understand. It's getting late and all that. So why would you? Why would you? Okay. So that's it. So we can close for the day. And the question and answer session is getting started in 33 minutes. And that's it. So would you not like to hear this multi-body system dynamics in 10 minutes? I mean, it's okay. It's not much. I haven't practiced it so much, so it's okay. So let's go and see each other in a question and answer session. And again, the first part is going to be in Finnish, and the latter part will be in English. Take it easy, guys. Have fun. Make sure that you are putting all effort in a midterm exam. And here's my last hint to you. Have a can-do attitude. All right? Can-do. Respect. We do respect with the can-do attitude. How bad is that? Pretty bad. Okay, guys. Take it easy.